All right, staying in chapter 6 where we deal with applications of integration, we're going to get into 6.2 here, which introduces a topic called solids of revolution, which for what it's worth ends up being a lot of students' favorite topic of the entire class, but then also a lot of students' least favorite topic of the entire class. It's kind of a strange one. It's different. It stretches the limits of your imagination to kind of visualize what's going on. We're going to be switching from 2 dimensions to 3 dimensions. So for some people that's awesome, they really like it, and for some it just never can quite wrap their head around this stuff and it's really hard. For what it's worth, we're going to be doing kind of the same thing just with two different methods in 6.2 and 6.3. So we'll spend a fair amount of time here dealing with solids of revolution. So the first thing you need to know when you're dealing with solids of revolution is, what do I mean by solids of revolution? And so what I'm going to end up doing in this video is this example here, which isn't a great example, but I'll explain its limits and I'll explain why we're doing it as this video goes on. But before I can even get to this example, I just want to talk about what I mean by solids of revolution. So the idea is, if I had a region, so for example, the region in between these two curves, or maybe not even the region in between these two curves, I could take some other region, like the region underneath the green curve, whatever I want. If I have some region in 2 dimensions, I could take that region and I could rotate it around something. So in this example, we're going to rotate around the x-axis. And you're like, what do you mean rotate around the x-axis? Like, how's that even possible? Well, it's not possible in the two-dimensional picture that I drew you. But if we had a third dimension, if you can kind of picture a third dimension heading out towards us, if off this piece of paper, then we could take any region and we kind of wrap it around this x-axis. It would come out and get closer and closer to us, and then it would get back and hit the screen kind of somewhere down here, and then it would go further and further away from us as it kind of travels behind the x-axis. If you can picture a region rotating around a line like the x-axis, you already have a really good intuition of what's going on. In case you can't, here's an animation that might help. So in this animation, we're not taking the region in between two curves, we're just taking the region underneath the square root of x. You can kind of see that in purple here. And we're 2 dimensions, the square root of x, we stopped at some point for whatever reason. And what I want you to be able to do is picture what would happen if we took this region, this purple stuff, and we rotated it around the x-axis here. And here's a video that kind of shows you what's going on. I don't know, that's way better than I could ever draw, but maybe you can kind of see that. That's just the outline of our solid. Here it is in more of a solid shape, right? That's what we'd end up with. If you started out with the region underneath the curve y equals the square root of x up to some x value, whatever this point is right here, and you took that region and you rotated around the x-axis, this solid is what you'd end up with. Maybe it helps to see it one more time. There's the curve. We stopped it right here, so we have this bounded region. And we talked a lot about bounding regions in the previous section. So all that stuff we learned in 6.1 about bounding regions is going to come into play in 6.2 and 6.3. But at any rate, you start out with any bounded region you want. We'll just pick on the square root of x for now. And then we rotate that. And when you rotate it around the x-axis, you want to be able to kind of picture this. And here it is, kind of the hollow version, and here it is the more solid version, whichever one is easier for you to grasp. And what we'll be doing in this section is figuring out the volume. Not the area, because it's not a two-dimensional region, but the volume. In 6.1, we figured out the area of this region. In 6.2 and 6.3, we'll figure out the volume of this region. So back to our problem. I found this problem online because there's a cool animation for it, so I want to use it. But first, I want to point out a problem with the problem. This says, find the volume of the solid resulting from rotating the area bounded by y equals the square root of x, y equals 1/10 x, and x equals 4. It didn't have this x equals 0 in there. So if you're just given these three curves, I think it's problematic. Like, I sketched the square root of x for you in green, and y equals 1/10 x, that's sketched in red. And if you think about what x equals 4 looks like, you just have to go out here to 4. So I don't know, maybe it's right here. This isn't drawn to scale. And x equals 4 is this vertical line right here. But there's a problem. When we talk about the region bounded by red, green, and blue, it's unclear what we're talking about. There's a region over here that's bounded by red, green, and blue, but there's also a region over here that's bounded by red, green, and blue because red and green intersect. Don't trust me that they intersect? If x equals 100, the square root of 100 is 10, and 1/10 times 100 is also 10. So when x equals 100, the height of both the red curve and the green curve will both be exactly 10. What I'm saying is the green and the red curve will intersect each other. So the problem, as you'll see it written in the video in just a minute that just involves these three curves, is problematic. It doesn't make any sense. I couldn't ask you that. But I suppose I could also say an x equals 0 or somehow indicate to the reader that it's this region that I want to rotate around the x-axis, not any of this stuff. At any rate, once you get to the point where you're like, all right, you want to rotate this region around the x-axis, we have to picture what it would look like. And I think that's really hard. And in a minute, I'll show you an animation that'll hopefully make that easier. But before I did, I want you to kind of picture it, right? This region, and we're going to take it and spin it around this line. What's going to happen? And what's going to end up happening is because the shaded region doesn't go all the way down to our axis of rotation, there'll be kind of a hole in the middle. Right? When you take this and you rotate it around the x-axis, if you can kind of sort of see a funnel, I guess, or a cup laying on its side. Let me show you someone who did a better job of this than I did. So this video, y equals the square root of x is this curve up here. Y equals 1/10 x is this curve further down here. The person who made this video doesn't bother pointing out, or maybe didn't realize, that these two curves are going to intersect each other if you go far enough out to the right. But whatever, then they throw in x equals 4, and that gives us this bounded region right here. And let's see what happens in this animation. There's the region again. You take this, and now they can kind of look at it in 3 dimensions. I don't know, I think that's kind of cool. If you were standing out here and looking inside, you'd see this hole, this hollow area in here that would come to a sharp point at the very bottom. It kind of looks like a cylindrical cone. And if you looked at this thing from the outside, it would look a little bit more rounded according to this y equals the square root of x. So you're like, all right, I can kind of sort of wrap my head around what a problem even looks like. But you haven't told me anything about how to answer that problem. Like, how would I possibly figure out the volume of this solid, which I can barely even visualize without the help of an animation on YouTube? Well, if we had to figure out the area that was bounded by these two curves, if this were a 6.1 question, then what you would do is you'd say, well, if I'm integrating with respect to x, my x's go from 0 to 4. So my bounds of integration will be 0 to 4. And then what I want to do is I'm going to kind of think about this like I'm adding up infinitely many rectangles. The rectangle is going to start at 0 and they're going to go till 4. And the height of each of these different rectangles, well, it's kind of the difference between the green curve and the red curve. So the height of the rectangles is not just the square root of x, it's the square root of x minus 1/10 x. If I think about any individual rectangle between 0 and 4, which is kind of sort of what this notation means, then if I had to figure out the area, I just add up those infinitely many rectangles where the height of those rectangles is given by this expression. If you want, you can kind of think about this as here is the width of the rectangles. It goes towards 0, it gets infinitely small, so we don't really do much with it. And here is the height of the rectangles. And of course, the height is going to be different for each value of x. So I got infinitely many different rectangles that are going to start at 0 and go to 4. And for each individual rectangle, I need to know the area of the rectangle. Here's the height of the rectangle. Here's the width of the rectangle. If that's the idea that you have in mind for 6.1, well then 6.2 follows a little bit more naturally. For 6.2, I want the volume, right? Not the area. So it's going to be a 3-dimensional thing. But instead of thinking about I'm going to add up infinitely many rectangles from 0 to 4, what I can do is if I think about any individual cross section between 0 and 4. So if I took the solid that I have, this 3-dimensional solid, so I know this is really hard to think about, and then I cut it perpendicular to my x and y axes. If I took one cross section of that shape that we saw in the last video, my question to you is what would that cross section look like? And again, that's a little bit hard to do, but fortunately the video animation goes through that. Here's where we left off last time we were watching, and if I go a little bit further, what you'll see is they explain exactly the calculation we're going to do. You take one cross section, so there it is, and remember this is infinitely thin here, but they give it a little bit of thickness just to kind of help you figure out what's going on. We cut this thing perpendicular to the x and y axis, and this is what one cross section looks like. And what is this thing? Well, it's a little bit hard to see when you see it like that, but if you spin it around, it's a little bit easier to wrap your head around. It's a washer. It's an infinitely thin washer. So we can kind of think about it as being a 3-dimensional thing or a 2-dimensional thing. It's really 3 dimensions, but one of its dimensions is infinitely small. Its thickness is infinitely small, so it's almost like it's 2 dimensions. But whether you want to think about it as 3 dimensions or 2 dimensions doesn't really matter. Think about like a washer, like nuts and bolts and screws, that kind of a washer. If you had to figure out the volume of that washer, what you would need to know is its thickness. And then you would take that thickness and you would multiply it by kind of the area of the front. If we could figure out how much area we have on the front here, and then took that and multiplied it by its thickness, that would give us the volume of the washer. And the good news is you can figure out the area of a washer pretty easy, because all it is a circle with a little circle missing. And I could figure out the area of a circle no problem, and then I could figure out the area of some smaller circle that's missing no problem, and then I could just subtract the areas of those two circles, and I'd essentially be done. Back to our picture here. If I take this arbitrary cross-section of the 3-dimensional solid that's created by taking this region and rotating around the x-axis, and I know that's a lot to ask with just this picture here, If you take that cross section, it's a washer. And the outside of that washer, I'm picturing it in green because it kind of comes from this curve. It comes from this curve, y equals the square root of x. And the inside of this washer, I'm picturing it in red because it's determined by this curve y equals 1/10 x. The very center of this middle circle, which is also the center of the outer circle, would live right here on the axis. If you can visualize all that, you can figure out the volume that we need, because all we're going to do is we're going to add up infinitely many of these washers. If I use capital R to denote the radius of the big green circle and little r to denote the radius of the little red circle, then all I need to do to figure out the volume of the washer is take the area of the green circle, which would be pi r squared, and then subtract the area of the red circle, because in my washer, the red circle's gone. This is hollowed out. So to get rid of this, I'd have to subtract pi r squared. This would give me the area of any individual washer, any cross section that I have here. And if I multiply that area by the thickness of that washer, which again is getting arbitrarily close to 0 here, I would have the volume of one of the cross sections that I need. But I don't just need one cross section, I need all of the cross sections together to figure out the total volume of my solid. Well, all I got to do to figure out all of them is let my value of x go from 0 to 4. So if I could write the outer radius and the little radius in terms of x, I'd have this set up as an integral that I could solve. And we can do exactly that. If you go back up to this picture, for any x value, the radius of the outer circle is just the distance from the axis to this curve right here. What I'm saying is for any given x value in between 0 and 4 here, the outer radius of my washer is exactly the square root of x. And the inner radius of my washer will just come from this curve, y equals 1/10 x. We can rewrite this formula, except in place of a capital R, we would have the square root of x. And in place of a little r, we would have 1/10 x. That gives us this expression, which represents the volume of the solid we're looking at. And if we could figure out what this is, we'd be done with the problem. And the good news is we're kind of done with the problem. The big challenge in chapter 6 is not evaluating these integrals. You can do this. This isn't hard at all. I know it looks kind of ugly right now, but we'll do a little bit of algebraic simplification like we always do. And then we'll be like, oh, that wasn't a bad integral to take at all. And then I just got to figure out an antiderivative and plug in some numbers and I'm done. This will not be the hard part. Like is often the case in chapter 6, the setup is the hard part. Figuring out that the volume of the solid resulting from rotating the area bounded by these curves around the x-axis is this expression. That's the hard part. But we'll do a lot of different examples, and what we'll learn to see is that it's kind of predictable that we have these two different curves, and the one that's up on top, if we're rotating around the x-axis, makes the outer radius, and the one that's down on the bottom makes the inner radius. And the area of the washer is always pi times the outer radius squared, and the minus pi times the inner radius squared. So a lot of setting this up will be the same in every single problem. So to evaluate this integral, maybe it would help to first notice that I have a constant in each of these terms. So I could, if I wanted to, pull that constant out in front and make this the integral from 0 to 4 of the square root of x squared minus 1/10 x squared dx. In fact, a lot of books, when they give you kind of formulas for this solid of revolution, they'll put the pi out in front. Because if this is always pi r squared and this is always pi r squared, you're always going to have this constant of pi in each of these terms. And pi, since it's always a constant, you can always just bring it right in front of the integral. I don't like doing that. I don't like starting here. I prefer to start with pi r squared, because when I write pi r squared, it's got me thinking in terms of circles. And then this has a little bit of an intuitive appeal to it. But you can do whatever you want. If you want to skip this step and jump straight to the point where the pi is out in front of the integral, you feel free. And then before I take an antiderivative to evaluate this thing, I should just simplify these two terms. The square root of x squared, that's just x. Negative 1/10 x squared, that's negative 1 over 100 x squared. And now when it's written like this, it doesn't look nearly as imposing. I can absolutely take the antiderivative of this. It's just a polynomial. I'll leave the pi out in front. The antiderivative of x is just 1/2 x squared. The antiderivative of negative 100 x squared, well, I'd leave the negative 100 out in front, and I add 1 to this exponent so it becomes an x cubed, but then I'd need a 1/3 out in front to make sure that the coefficients match, so I guess that would make this 1 over 300 x cubed, and then I just need to evaluate this thing from 0 to 4. And evaluating this from 0 to 4, well, if I plug in 4s, 4 squared is 16, 16 times 1/2 is 8, and then 4 cubed is 64, and 64 over 300 is, well, I don't know, maybe 64 over 300. And then from that, I guess if I want to write out all my steps, I will plug in zeros and I'll get 0 minus 0, and you don't even have to write that if you don't want. The point is just my final answer is whatever 8 minus 64 300ths is times pi. Let's see, 8 over 300, I guess if I got a common denominator, it'd be 2400 over 300, and then I have to subtract 64 over 300 and multiply that by pi. And subtracting those two numbers, I get what, 2336 over 300. I don't even want to do this. You get some number, you can figure out what that number is. You can write it as a fraction that's not reduced. I don't really care. The point is not so much what this answer is, and more how you can do this problem. And doing this problem, the stuff in green really isn't even all that important. It's can you get to the stuff in blue? Because if you've been following this class and gotten to chapter 6 and keeping your head above water, the stuff in green is fairly easy at this point, but the stuff in blue is not. So what do you need to take from this video? Well, I guess if you wanted a general formula, the formula that I think would work out best for you is that the volume of a solid of revolution, we're going to integrate from somewhere to somewhere with respect to some variable. In this case, it was dx. But what we'll see in the next video is we can rotate these around the y-axis, and then we'll want to integrate with respect to dy. And all we got to do is take pi times the large radius squared and then subtract pi times the small radius. This isn't a great formula because I have the letter r written in here and it's not even defined, and my variable of integration is x. So what's r in terms of x? Even though this isn't a great formula, I think that this is, if you can leave this section with this idea making some sense to you. Okay, I got infinitely many washers, and the volume, if you want, of each individual washer is the thickness of the washer, which is negligible, times the area of the washer. And to figure out the area of the washer, I'm thinking the area of a big circle minus the area of a little circle. And the big circle will be given by one of my functions, and the little circle will be given by one of my functions. So all I'll have to do is plug those functions into this formula, and then I'll be good with it. Before I finish this video, I want to make two more comments. The first one is kind of shout your book out a little bit. They do a much better job than I can do of drawing pictures. And even though they don't have the animations handy, I don't know, maybe they do. Maybe there are some links to animations somewhere associated with this book. I'm not sure. But the point is, I think that this picture, after watching the video that you just watched, might now have a little bit of meaning. We're going to have some region that will be specified in much the same way it was specified in the previous section. And we're going to rotate that around some axis. Let's start with just the x-axis for this video. And that will give us this three-dimensional solid. And if you can get to the point where you can take this picture from 6.1 and see this picture from 6.2, that's really good. So if I took this region and I rotated around the x-axis, I'd have this three-dimensional figure, this sort of cup laying on its side that's hollow in the middle. And what I need to do to figure out the volume of that cup is add up infinitely many cross sections. And so you're kind of picturing this cross section in pink here, which they denote here. And they're like, hey, good news, this cross section, because of the way we formed this solid in the first place, because we made it from rotating around the x-axis, this cross section is going to be a washer. And the area of a washer, just pi r squared minus pi r squared. One last comment. Sometimes the bounded region that we're looking for stretches all the way down to the axis we're rotating about. We saw that a little bit in this example, right? In this example, the region that we started out with went all the way down to the x-axis. So when we rotate it around the x-axis, we end up with a solid that doesn't have the hole in the middle. And you're like, whoa, what do you do if you don't have the hole in the middle? That sounds like that's going to be harder. It's not. It's way easier. There's less to do. This second case that I'm talking about is actually simpler than the first case, because if you take a cross section here, as this video is about to do, it's not a washer anymore. It's just a disc. So it's even easier. Now, all you have to do to figure out the volume of this disc of any cross section in here is, well, it's just going to be the area of this circle times the thickness. And the thickness is just going to be dx. So really all you're worried about is the area of the circle. The point I'm trying to make is that if you're lucky enough for your bounded region to go all the way down to the x-axis, well, then there is no lower curve. So it kind of makes sense that there is no smaller radius. All I would have to do is take pi capital R squared and multiply that by dx and be done with the problem. This section is called discs and washers, and the reason it's called both discs and washers is because there's a simplified case where a cross section actually isn't even a washer because there's no hole in the middle, it's technically a disc. But I think it's easier to just think about the washer case as kind of your base case, and then remember if you ever run into the disc case, it's even easier and you don't even have to worry about the inner radius.